Well, Tony, do you want to go to Q&A? Does anyone have questions? If you're open to it.
Yeah.
Oh, okay. Yeah, and actually I had someone before the conference, and I forgot who, had asked. Let me scroll down the list and see if he's still here. I think it was William Schramm. William, you had some questions about superconductors before the conference, right?
Hey, let me bring the video online. Yeah, so my questions were really, can this physics be evaluated with Gen 1 superconductors? Is it possible to use niobium instead of yttrium barium copper oxide?
I don't know that anybody can answer that because no experiments have been done. Even on the YBCO, you know, no one has really ever repeated what Pekletnov did. Anybody who claims they have are lying or stretching the truth a little bit. I can't speak to what might have happened in projects that were classified, but I really don't think anything was done there either. But it's hard to say. If you read my paper in that gravity book that we did, then I tell you why a superconductor could create a gravity wave. But it could be any superconductor. It doesn't necessarily have to be. Well, I'll take that back. It probably has to be a type 2 superconductor, and the reason for that because of the flux pinning that goes through the superconductor. Those pinning sites are actually they're more superconductive actually than the superconductor itself. In fact, electrons can move through these pinning sites faster than the speed of light theoretically. So it may need to be a type 2 superconductor for this effect to occur.
Okay, and then the follow-on question to that is, well, what vendor do we go to for a disk like this, or do we have to make it ourselves?
The last time I looked, there wasn't hardly any YBCO superconductor manufacturers in the US. They were all over Europe, but it's not hard to make a YBCO superconductor. In fact, I came up with a formula for making the superconductors from the powders that was different than what you read online, read about in other literature, because the barium oxide, first bottle of barium oxide I bought, I opened the thing up and began choking immediately because that barium oxide wants to turn to barium, turn into a hydrate, so it sucks the oxygen out of your nose. And everything. So I immediately said, I'm not using that. And so I went and started using the barium hydrates. It's a different formula, but it came out very well using it. In fact, you could, once you do use the hydrates, you can actually mix it with water. Where if you I took some barium oxide and put it in a glass beaker and poured water in there, and it almost melted the darn glass at the bottom because the heat it created from absorbing the water and turning into the hydrate was so hot. But anyway, it's not hard. I can do it at home. I can get a little furnace here. I've made superconductor powder here at home.
Okay.
Yeah. Now, so if I could jump in really quick, William, one of the things that I mentioned to you, and this goes back to before the call because you were asking about superconductors then. Tony, as I recall, and I might be mistaken, but hadn't you said that there was a skin, that the crystal inside of the bulk of the superconductor is different than the crystal along the skin? And there was something about, if I remember right, there was something about the construction process that made that skin more important.
Well, Pekletnov supposedly did the 2-layer, where the bottom layer was not superconductive at the 77 degrees of liquid nitrogen, where the top layer was. It was so if you dope the bottom layer with say YBCO instead of yttrium with a Y, dope it with like praseodymium or something, then it drops the superconducting temperature lower than the 77 Kelvin. And then the top layer would be YBCO, but then it was supposedly melt textured, where they actually put little seeds of a different type of superconductor on it, usually where they're yttrium replaced with samarium, I guess, on top. And then what they did, the melt grows. And so that crystallization should form across not only the YBCO top layer, but also the non-superconducting second layer. So the crystal growth through the whole body was not just not just centered superconductor, but a crystallized superconductor. And that can be important because in this crystal, it actually, the crystal forms layers of these Josephson junctions throughout this crystal growth. And I think why those Josephson junctions are important to get the rapid electron motion to the superconductor.
Awesome. Thank you. William, did you have any other questions, sir?
I guess my question was, my experience is working with a German vendor on wire. And so they actually strained the wire in order to create the crystal boundaries. Is there any research into when you're making a disk, manipulating it in a way that creates those crystal grain boundaries?
Well, the only thing I know about crystal growth is that melt texture crystal growth. I mean, this was back in the late 1990s. There should have been a lot more research done since then, and the way they're doing everything. But as far as the experiment Knuth did, it was just simple YBCO melt textured with two layers, that one superconductive at 77 and one not. So.
Okay, great, thank you.
Wonderful, thank you, William. Gary, let me go to you next, sir.
Sure, yeah, I was wondering, Tony, if you've had any contact at all with George Hathaway. My understanding was he was trying to replicate the same experiment a number of years ago in Canada.
Well, I don't think he did the rotating one, but he did attempt the impulse one. And it's my understanding that the disk he used for the impulse was not two-layered. It was not I don't know if it was the same size or not, but it's been a long time ago, so but what I remember is that he didn't do the experiment to the degree that Knuth did.
He never did the spinning one, in other words. Huh? To your knowledge, he never tried to replicate the spinning superconductor.
No, making a 12-inch superconductor disk is quite difficult, and which we learned, and making it two-layer is even more difficult. And then putting it in a furnace and doing it. We never got to the melt texture. We never got to two layers. The group down to the SBIR did, but we never did. And so making something that large that comes out of furnace that's not cracked is just a miracle.
To your knowledge, George never got that far.
No, but he did do a version of the impulse experiment and didn't see anything, but I don't believe the superconducting disk was the same as that Knuth reported using.
Okay, thanks.
Okay, thanks, Gary. Let me go to Harold next, sir.
Yes, Tony, thank you for that explanation. That clears up a lot of things because I know that Ning Li got a lot of publicity, but you make a lot of things clear now. And my question for you is this, that experiment that Ning Li was supposed to do, if it would have been you that had to do it, how would you have done it? And the other part of the question is, do you have a theory, a propulsion theory on how to use a superconductor to create, for example, artificial gravity waves, or a propulsion system? What are your thoughts on that?
You're asking a lot of questions that I don't think I can answer in this time frame. But first off, the experiment that everybody says it was Ning Li's was not Ning Li's. It was NASA's, Marshall Space Flight Center. She was part of that team. In fact, like I said, the experiment she brought to Marshall Space Flight Center wasn't even her experiment. It was Robert Becker's experiment, and actually a UAH student who did it as a thesis project. So when people say it's her experiment, it wasn't. She was just part of the team to do this. She was tasked basically in the first part in the Senator Kreshner Fund projects, which I support her on that. She didn't do much of anything. I did most all of that stuff. And then when we went to the Knuth experiment, she was just tasked to actually take the disk we pressed for her at Marshall with using the disc that we bought under the project. And she took those discs back to UAH and fired those discs. And then she was supposed to give those discs to us so we could analyze it using NASA's expensive technology they had there and see what the structure was. And so we can determine if we were actually making something correctly, but she would not give us anything she fired. So we couldn't do anything. Money ran out. We didn't have discs for her. We made some ourselves and played and stuff, but we never could. Like I said, once that team was formed, there was no accountability. You had 5 people going in 5 different directions and with no clear path on where we were going. And so that just failed. And then the SBR one had a clear path, but they got so focused on spending their money getting off, and then they, like I said, they bought a $60,000 doer that was just terrible, and they wasted a lot of money and couldn't finish the project. They helped Kletnoff out, but they didn't help us out. So, but as far as the theory, I've sent you my papers, but on A theory, but that one doesn't really talk about superconductors. But if you read my paper that's in that superconductor gravity book, it tells you why a superconductor could give you a gravitational wave. What else did you ask?
Actually, Harold, if it's okay, let me jump in really quick. Tony, can I put your book up on the screen? Can you tell me what the title of your book is?
Yes, yes.
Superconductor, crap, I don't even remember what the title is myself. Gravity interactions, superconductor gravity interactions, something like that.
Okay. It's available in Amazon?
Yeah, I can send you.
Here we go. Okay, and let me see. And you know what I will do? Okay, give me 2 seconds. I will share I'll share my screen again. And my apologies for jumping in and distracting. Okay, so here it is. I will paste this into chat, but for anybody who's watching this in replay or can't see it, it's Superconductor Gravity Interactions, published February 12th, 2018. I will maximize that there.
They were supposed to send me money when they sold this. I haven't made a dime off of it. This was published in 2012.
Yeah, so that is up here. I found it on Amazon, and let me see. The authors are Giovanni Modenese and then of course Glen A. Robertson. So okay, and again, my apologies for disrupting things. Harold, did you have any more questions, or should we go to Jeremy next?
Hey, thank you for the explanation. That clears up a lot of things.
Okay, wonderful. Well, thank you as well, Harold. Jeremy, would you like to go, sir?
I'm having issues with my stream microphone, so people might not be able to hear me live on YouTube, unfortunately. I had a question just about so apparently the size of the superconductor disk was the issue, like making them that large, and apparently they would crack or other things would happen when you try to make them that large. Is there any processing or any special techniques that we should know if we're trying to build a large diameter disk to reproduce this experiment accurately?
The pressure that you have to press these to is like 20,000 pounds per square inch. So we were using like a 1,000,000-ton press that NASA had that actually were used to test some piece of the launch system for the shuttle. and if you don't press it to this, then it's not as dense when you put it in the furnace, so it wants to shrink, and so when it shrinks, it cracks. Even a lot of the smaller ones I made, rather than being flat on both surfaces, would be curved on the top, because the heat would be hot around the outside, so it would harden first on the outside and then sink in the middle on the smaller ones. So pressing is a key issue, and a press that big is not available to everybody.
Okay. Okay, Jeremy, thank you. I think Jeremy just dropped off the call. Let me go. We'll probably try and do 2 more questions if that's okay. Let me go to Michael Boyd next. Michael, sir.
Hey, so I have a couple of questions. One is that I'm curious. You talk about pressing it, and my understanding is there should be a relationship between the amount of pressure that's put on the superconductor and the properties of superconductivity. I think there's been some recent research where they've actually achieved like room temperature superconductivity, but only under high pressure. Do you have any thoughts on that? And then the other thing I'm curious about is as far as it relates to the gravitational field, my understanding has superconductivity, the way it works is it's kind of like antiferromagnetic. So it's
all right.
It's only on the outside of the superconductor. It's a surface phenomena. It's nothing in the there's basically no magnetic field inside the superconductor. So I'm just curious what your thoughts are about that.
There's two different types of superconductor. One's a type 1, which exhibits the Meissner effects and excludes all magnetic fields. And then there's a type 2, which is what the YBCO is, that actually pins the fields inside of it. In fact, you can take a type 2 superconductor and cool it under a magnetic field and then take the field away, and it'll still act like a permanent magnet, even though
so it's kind of like a magnetic dielectric, you know, how like with a capacitor, if you have like a dielectric material, you can charge it up and move it around and like plug it in.
Yeah, you can.
Kind of like that.
I actually did experiments where I pinned the fields in the superconductor and then mapped the field that was on top of inside the superconductor. I actually did those experiments to show that. And this pressure you're talking about, it sounds like what you're talking about is not a pressure to press the material into making it, but to the pressure in a chamber where they're testing it in a chamber pressure. So
it's in a pressure environment. Physical pressure during the when you're measuring the superconductivity.
Right. Yeah. Mm-hmm. It's two different things. So.
Okay. Thank you.
Wonderful. Okay. Well, let's go to William Schramm, and then after that we'll wrap up questions. So William, why don't you go ahead, sir? And then after that we'll go to Mark.
Just one more question. So instead of a disk, could you have just replicated this using a loop of wire? If you could anneal a length of wire to make the loop instead of a slice of a cylinder, would that generate the same effects, or does it have to be a three-dimensional, have some depth to that plane?
Well, according to the paper I wrote that's in the book, it'd have to be a solid disk because from my perspective of the paper is that you have to have these Josephson junctions. That's what's important because the electrons can move across these junctions at very fast speeds. And in a wire, you wouldn't have that. And the currents you would be putting in there, if you're talking about a wire, are going totally different directions. So, but it's not to say it wouldn't show some kind of effect. I just don't know.
Okay.
Wonderful. Okay, so let me go to Steve Lutz really quick, and then after that, and again, my apologies, I'm trying to juggle time here a little bit. Steve, why don't you go for it, and then after that, we'll go to Mark Sokol.
Yeah, sure. I just have two questions. One, do you know who the program director was for this SBR?
For the SBIR, Ron Kozar from NASA was the one who initiated it. So I would say he was the NASA manager part. But the SBR program itself has a manager at a headquarters.
Right.
So who's actually in control? I couldn't tell you.
yeah, that's a lot of these programs. It's money goes out the door, right? So you were peripherally involved, like in a support capacity, or directly involved with this whole thing that we're doing here?
When Ning Li came to Marshall, I was the one who wrote all the proposals for going to the NASA management, but I wasn't at that time part of preliminary design. I was still in the propulsion lab at that time. So Joe Howe was actually the guy put on as the PI.
Okay.
for those Senate discretionary funds. But I'm the one that actually wrote the proposals and did most of the work. Joe Howe was the one who found the manufacturer for the die.
The YBCO.
Yeah.
Yeah, I mean, I started my career as a specs writer and the proposal writer, so I know exactly what you're talking about. Yeah. You're just cranking paper.
Right, but by the time I moved to preliminary design, we'd already formed this team and gave basically the lead to the science directorate. And once that happened, like I said, it was just 5 people going in 5 different directions.
Right. So no EDR, no engineering design review kind of thing. It was just sort of go for it, right?
If there was any, if there was anybody reporting to management, they didn't invite me. I wasn't.
Yeah, I'm in the same club. I never got invited to like once or twice, and they said, shut up and don't talk,
But we spent so much money on it that no one wanted to ask for any more to continue going.
It's embarrassing, right? Because you blow out that money and no results, and then it's the blame game, right?
Yeah.
We used to have the wall of blame and the wall of shame. The pictures of the people. So my other question is this: the YBCO, are you privy to the crystallinity of it? I mean, the manufacturing process, would they cook it slow and then hydraulic press it? Was it polycrystalline? Was it high order poly? Was it near mono? Do you know any of that stuff?
I know how to make the superconductor. I know how to press it. I know how to melt texture. I've done all of that. Yep. The disc that Kletnoff actually had, from my understanding, he did not make the disc. He borrowed it from somebody else.
Correct.
Who made the disc and literally didn't know much about the disc at all. That's the reason why when they went to the SBR and hired him, he kept having them do this and that and was wasting a lot of money for him, basically, to learn how to make a disc for himself. But the disc, basically, making the powder is, you just take the raw materials, you mix them together in the right, in your furnace, there's a heat profile you go through, and then it comes out and it's centered a bit. You have to crunch that up into a powder. Then you take that powder, put it into your die, press it, like I said, to 20,000 pounds per square inch. And then you take it out of your die and you take that and put it in your furnace and heat it through a temperature profile. And if you want to melt texture it, you have to go redo that with these little seeds of a different type of superconductor on it.
That's all correct.
Crystalline growth. And the crystalline growth is actually the 8-sided
yeah, it's hexagonal. That's correct.
Hexagonal, and it starts out like a pyramid and goes down through the materials.
Yeah. So, and one of the things you got to do is mill it for like a day or two, right? So when you get the powders and everything, you got to mix them, just keep it going.
That's the way you normally do it, but that's not the way I did it. I just grounded it up till it looked like a nice powder and shifted it through some sieves. And when I got enough that went through the sieves that looked okay, I forget what size, but very small grain sieves.
Right.
I think it's micrometers that you had to take it down to.
You get these micrometer crystals, and then you grow it low and slow in the sintering.
Yeah, it takes days, even weeks if you do the.
That's right.
Put it under oxygen to oxygenate it can take you a week long to do that.
Yeah. So what I've seen is that if you can get the crystallinity up instead of like polycrystalline, if you can get the crystallinity to be more organized, you can get some more interesting effects out of the material. And spinning is not a thing. It's not. I know Kletnoff thought it was a thing. Spinning is critical. It's actually turns out not to be the case.
I don't think Kletnoff was originally doing this experiment as a superconducting gravity experiment.
No.
From my view, this is just my view of it, I think he was actually trying to do an experiment to see if superconductors could be used as a radar deterrent type of material.
Yeah, it was a military thing. That's right.
That's the reason why he was hitting it with RFs, is to see how the signals would come back. And what had happened was a professor had come in there smoking or something, and the smoke
that's all correct. That's 100% right.
So his initial experiment was not a gravity experiment; it was something totally different.
Yeah, he told me directly what happened. It was exactly what you say. It was a military thing, for the anti-radar, low observable stuff. The guy came in smoking. As if you work in these labs in Russia, and I have, and in the former Soviet, everybody comes in smoking and drinking after hours. Everybody,
The,
you know, it's cognac, it's smoking. Yeah, it's hilarious.
Everybody smokes.
And they noticed the smoke drifting up, and then they went upstairs and they saw it was still going on, and they went up to the roof and they saw the effect was still there. So in the end, yeah, I mean, he's a metallurgist kind of guy. He's a master's guy, right? So the guys that made the actual disc he was playing with were another group altogether that knew what they were doing. But I'm always fascinated and interested in the crystallinity, because when I looked at something that, for example, Claude Poher was doing over in France with this YBCO, he had even worse crystallinity, but he did multi-layer. You know, he did like 12 layers, I think, when I was there.
I've been to Poher's house in Spain.
Yep. And some interesting effects came out of it. But they're all using pulse Marx generators.
No.
Everybody, right? So Marx generator, they do a pulse. It's 100 milliseconds or so, 10th of a second.
That was the impulse experiment he did, not the rotating one. Yeah. And Poher's experiment, like I said, I've been to Poher's house in Spain. I saw his experiment there. And he basically was just making a big arc in liquid nitrogen that was blowing the liquid nitrogen around. And some guys at Marshall actually repeated the experiment, and that's the same conclusion they did. And that was the conclusion I came out of Poher's house with, is that it was just an arcing effect.
Right. My thinking is that a sustained DC with an AC ripple and the AC ripple being at a high frequency, perhaps terahertz range, something like that, might yield some, I don't know, interesting results if we were to try it.
Yeah, terahertz is an interesting range to be in, and it's just relatively new as far as being able to do that. So
you can get the terahertz generators right now. I looked it up, but it's just a handful. They're very expensive, and you got to, you know, you have to know what you want. You know, you talk to the manufacturer, you say, I want something that does this, and they give it to you. But I say, if you want, I want something in a range. Well, we can go, no, we can't do that.
It's still relatively new technology. They were developing it years ago. I was reading articles where they're trying to develop terahertz sensors to penetrate the ground to find tunnels.
I saw that. Yeah, I was looking at indium phosphide as a possible candidate to do that. But again, you know, I talked to a manufacturer about it, and they're like, "Yeah, we're doing it for high-speed switching. That's it. You know, where's the money?" Right. All right. Thanks. Appreciate your answers.
Okay. Thanks, Steve. So let me see. Mark, are you ready? Or let me ask Mark.
Yeah. So I'm trying. I have a little surprise for you guys here. I'm trying a replication.
Well, let me. We should say thank you to Tony first, and I should apologize for that. Okay.
Thank you.
Yes, okay, well, so let me do that then. Let me do that, and we will come right back to you, sir. And again, okay, so what I'm going to do is, before we do anything else, let me go to gallery view. And everyone, please put your hands together and give Tony an enormous hand. Thank you. Tony, thank you very much. It's wonderful to have historical insights into the past research that's been done, and actually I'm really excited. So let me put, and I should apologize that we kind of ran out of time there. Let me put the hands down there, and